Fraser got a problem with me.
There you go. All right. All right. So 4.2, number 13. The elevator is going up at 10 meters a second. Thank you for reminding me. Let's see. It says. Oh, God. Hello, Miss Records. Hey. I cannot. She's not here. I don't know where she is. Yeah. Okay. Yep. Bye. Okay. All right. Let's see. So it says a boy on the elevator shoots a ball directly upward from a height of 2 meters above the elevator floor. So the position of the ball relative to the elevator initially is 2 meters. Is everybody okay with that notation? Let's see. Just as the elevator is 28 meters above the ground. So the position of the elevator relative to the ground initially is 28 meters, right? Let's see. The initial speed of the ball with respect to the elevator is 20 meters a second. So the velocity of the ball relative to the elevator initially is 20 meters per second. Okay, so that is all the information that we've got. I guess I should probably make a note, because it's important, that the velocity of the elevator relative to the ground is, in fact, constant.
Will they always be? Under test?
Yes.
I didn't want to say that.
Okay. All right, so are we all good?
Yes.
Okay. All right, so A says, what maximum height above the ground does the ball reach? All right, so to answer question A, everything about question A is relative to the ground, right? So I want to keep track of the velocity of the ball relative to the ground and solve it as just a regular kinematics equation, or regular kinematics problem, rather. So for part A, what's the velocity of the ball relative to the ground going to be initially? What do you guys think? Let's see. Well, that's the velocity of the ball relative to the elevator initially, plus the velocity of the elevator relative to the ground initially, right? Let me pause there for a minute.
Is the elevator going up or down this round?
It's going up,
All right.
which we know for two reasons. One, because I made the velocity of the elevator relative to the ground positive.
Second, it says it's ascending.
And secondly, it says it's ascending, which means going up. All right. Is everybody good so far? Okay. So basically, it's this. Look, the elevator or the ball is being thrown at 20 meters a second, but it's inside an elevator that's moving at 10 meters a second. So that means that at the instant we release the ball, it's actually moving up at 30 meters a second relative to the ground. Cool? All right. Now, we want to figure out how high it's going to go, right? So we're looking for the displacement of the ball relative to the ground, right? During what time interval? Or what else do we know? There's two other things we know. Thoughts? Sure, what do you got, Dana?
You can find the initial position of the ball relative to the ground if you add the displacement of 28, right?
Sure. So the position of the ball relative to the ground initially is, well, I mean, I guess if you wanted to be, this is sort of a little notation heavy, but it's basically 2 plus 28, right?
Right.
Do I need to say more than that? I mean, do you guys see that you're just doing BE plus EG equals BG? Everybody cool? Anybody unhappy? Okay, cool. What are we trying to find, though? We're trying to find the displacement. Be more specific. Anytime I say, oh, we're looking for displacement, you should be asking yourself, what displacement? So displacement of the ball, great. Relative to the ground, great. But so anytime you talk about displacement, anytime you talk about change, you're talking about a time interval. So what time interval? From the time he throws it until until it gets to the top. So the final velocity is 0, right?
Yes.
Does everybody understand that? Okay, so we're looking for a time interval. We want our velocity of the ball relative to the ground final to be 0. And there's one other thing I know. What else do we know, you guys?
Acceleration.
Acceleration, right? All right, so here's the stuff we know. We know our velocity initial, we know our velocity final, we know our acceleration, we're looking for displacement. Hopefully this is becoming second nature to you by now. We got to use this guy and solve for our displacement, right? Just by plugging in our numbers. So you can get 2 times negative 9.8 times displacement equals 0 squared minus 30 squared, and solve it. And it gives you not the number that's on the sheet, because you have to add. It gives you 15.9 meters, I hope. Do I believe that?
No, you changed it. It was like 75 point.
Oh, did I change it? Okay. Okay, gotcha. Oh, right, I gotcha. Okay, so that's 45.9 meters. Thank you for reminding me. Okay, so that's your displacement. Does that make sense?
Yeah.
All right, and then we got to add on the 30 meters, which was the mistake I made, to illustrate the fact that it started at a point 30 meters up, right? Good, you guys?
So you added 30?
Yes.
So the real answer is like 75?
75.9, yeah. I think I made an announcement about that the day we went over it.
Got it.
So if you want, you guys, mathematically it's this. Your final position is your initial position plus the change in position, right? So 30 plus 45.9 gives you 75.9. Problems. Okay, part B. How long does the ball take to return to the elevator floor? So, whole new frame of reference, right? So now I want to keep track of stuff relative to the elevator floor. So here's what I know. The velocity of the ball relative to the elevator initially was it 20? I know that the position of the ball relative to the elevator initially was 2 meters. I want to find out how much time it's going to take to get where? What are we trying to find, you guys? The time for it to do what? Get back to the elevator. So how do I, using my stupid many-letter notation, how do we write that? I want the position of the ball relative to the elevator final to be 0. Follow? All right. Now, we don't have very many equations that have position in them. Usually we have change in position, right? So really what this is telling me is that I want the change in position of the ball relative to the elevator to be negative 2 meters, right? Because we want to go from a position of positive 2 down to the floor, which is 0. Cool? And then you know your acceleration is negative 9.8 meters a second squared. So, there are 2 ways to do this. You can do it using the quadratic formula, which I actively dislike. Or you can use this guy to find your VF as it hits the ground, and then find the time to get to that VF.
And the VI in that case would be VEI?
Yes. Because relative to the elevator, that's our initial velocity. Follow, you guys? So here's the deal with this. Because we're doing everything here relative to the elevator, and this is huge, you guys, because we're doing everything relative to the elevator, the fact that the elevator is moving doesn't matter. Because it's moving at a constant velocity. Follow? Everybody good? So this is basically, Roy throws a ball from a height of 2 meters above the ground up into the air at 20 meters a second, how long does it take to land? That's all we're doing here, okay? So let's solve this thing real quick. So you get 2 times negative 9.8 times negative 2 equals VF squared minus 20 squared, and solve that, okay? So when you do, you're going to, add 20 and take the square root. When you take the square root, you get 2 answers, right? Positive or negative. Which one do I want? You want the negative one. So this is going to give you negative something. Cool? I'm going to trust you guys can all do the algebra there. All right, and then we can find our time just by doing VF minus VI over A. So our VF is the negative something that we just found. The VI is 20, and the acceleration is negative 9.8. That gives you your answer. Good or no? All right. So what would make this problem significant? Well, not significantly. One level of difficulty more challenging, that was a terrible sentence, is if the elevator was accelerating. Okay? But it's honestly not that big of a deal, because then you just find the acceleration of the ball relative to the elevator using the same rules that we use for velocity or position. Okay? All right, are we good? All right. The other one I wanted to talk about was number, and I hope you guys are okay with the fact that I picked a couple. And I know you guys have questions too, so I'll make sure we get to those. So on section 4.4, number 14, I don't think we did this one last week. Am I right? We didn't do this last week, did we? No, we didn't. We didn't. Okay. So, I guess let's just go through it. So, it says a particle is in uniform circular motion about the origin of an xy coordinate system. So here's my coordinate system, here's my uniform circle. It's moving clockwise with a period of 7 seconds. At one instant, the position vector measured from the origin is 2I minus 3j. Okay? At that instant, what is the velocity in unit vector notation? All right? So basically, I just wanted to make sure you guys were good with the geometry of this. All right? So, yeah, in that we're talking about shapes and angles and... Okay. So let's do this. We're moving in circular motion, right? Uniform circular motion. So I ought to be able to find the velocity by using just, how far it travels dividing by the time it takes, right? Is everybody cool with that equation there?
Yeah.
All right, but before I can do it, I got to figure out what my radius is, right? So, and do you guys know, please make sure you're aware, I can't just plug this in because that's a vector, right? And remember, this equation is just good for the magnitude, right? Okay, so how do I find the radius? It's just 2 squared plus 3 squared square rooty, right? So root 13, whatever that is. Just had a calculator that I sat down somewhere stupid. What's up, sir? Yeah, sure. Okay, so root 13 to the 0.5 power gives you 3.605, we'll call it. 3.606, I guess. Okay, so there's a radius, so now I can find my velocity, right? It's going to be 2 times pi times that radius divided by 7 seconds. And it gives you a velocity of 3.236 meters a second. So that's the magnitude of the velocity. But the question wants to know, how is it worded?
Vector notation.
Yeah, in vector notation, what's the velocity at that instant pictured? Good. So, how you do this, there's a couple options. There's a way to do it using similar triangles, which, to be honest, I think is the easiest way. But I'm worried that it's not the way that would occur to most people to do it. So, honest question. Do you want me to show you how to do it just using, like, geometry and some basic trig? Or do you want me to do it using similar triangles? Or both? Okay, geometry and trig. All right, so let's do it. All right, so check it out. So here's the deal. Point for me. What direction does my velocity vector point in? Remember, it's going clockwise. So this way, right?
Yes.
So there's my velocity vector, right? Okay. So do you guys agree that I can find... Here, I need to embiggen this drawing here.
It's going down to the left one, the answer both 3 times -1.
There's our R. Yeah, this was, remember I told you guys that I had the signs wrong on my answer?
No, I don't remember.
Okay, I did say that, but we seem to be doing the two that I got mixed up on. Okay, so we know that this was what? 2I minus 3J, right? Okay. Do you guys agree we could use a little bit of trig to find that angle there?
Yes.
Right, because let's see, this is going to be -3. This is 2, right? So I could do inverse tangent, right? So let's find out what that angle is using the calculator that I keep setting down in a different place every time I use it. Inverse tangent of 2 divided by 3 gives 33.7 degrees. Follow? All right. Well, that means that this angle here is 90 minus that, right? Which then means that this angle here is 90 minus that, so you get 33.7 again.
Hang on.
Okay, so here's maybe the thing that I glossed over that I may have lost you guys on. What is true about the R and the V vectors?
Oh, they're at 90 degrees.
They're perpendicular.
That makes
Is that the piece you're missing?
Yeah.
Okay, so this angle here that I just traced out in black is 90 minus 33, which gives you some number. And so the right angle is 90 minus that again, which gets you back to 33 again, right? Follow? All right, so now, since I know that this velocity vector was, what did we say, 3.206 or something? Meters a second. And now I know the angle, now you can split it up into vector components. Okay? Yes?
Couldn't you just like leave the radius in vector components and then do like
We set up a ratio.
components? No, like when you're finding the velocity in its components and then just like do the equation on
Doing this?
Then you get the components of velocity and then you do everything.
Does that? I don't believe that that works. Because this gives us the magnitude of the velocity. It's not a... No, if you do that, it switches your x and y components. I remember somebody tried this when we worked on it during the tutorial. Okay? So the answer you should get here is whatever I said on the answer sheet, except I've just got my signs flip-flopped. So it gives you negative 2.69 I minus 1.80 J meters a second. And Maggie, I'm guessing you got the 1.8 is your I. Okay. All right. So do you see why that doesn't work, Maggie, or no? No? So what you're saying is you did this. 2 times pi times, and Seb, I'm not ignoring you. Let me just finish my train of thought here. You did that, right? Shh. 2 pi r over t, is that what you're saying? What? Right. So so the problem is, you guys. All right. So because this is a vector and everything else here is a scalar, when you solve this, what you end up getting is a new vector in the same direction as your radius. Like if you multiply a vector by a scalar, which is what I'm doing here, vector times scalar, then you get a new vector in the same direction as your original vector. Okay? So in other words, this would make my velocity vector this way, pointing in the same direction as my radius, which it's not supposed to. Okay. All right. So, what's up?
Could you finish the problem?
Oh, yeah.
I don't understand how you get from there to there.
Well, so now we've got this new velocity triangle, right? Our velocity is 3.206 meters a second. Are you good with how I got that?
Yes.
And then there's
And then your angle there.
a horizontal component and a vertical component. And this angle here is 33.7 degrees. And so then you just do, sine, cosine.
Okay. So it's like this little angle there. Why is it that angle there? Why is it this 33.7 red?
Say that again. Y is what?
I know that. I know. You know. All right, I see it now. I see the visual.
Are you okay or no?
Kind of. I can't see myself doing this right on without that. But I mean, I'll figure it out.
Okay.
Yeah, or the radius meets the velocity line.
Yeah, where? Okay, so while they're sorting that out, is everybody else good? I almost used the word copacetic. I don't know why. Everybody happy? All right, it's a good word. Copacetic. It means, is everything good? Okay. All right, cool. So those are the ones I wanted to talk about. What ones do you guys want to talk about? And when do we get out of here? I have no idea.
15.
15? Oh, right. Good. We have 10 minutes. All right.
No, I don't know.
Oh, 9? Okay. What do you got? Sure, what do you got, Sarah?
Can we do another relative?
Another relative motion one? Sure. Sure. Yeah.
That's a good idea.
I think we've not. Did we do number 9 yet? Take a look at number 9 and tell me if we did that one. I don't think we did. That feels like a good one to do.
Oh, yeah, that is a good one.
15 is straight out of the notes. If I hadn't done that one in the notes, I would do that one. I really like number 15. If you didn't just hear me, I said I really like number 15.
And
4-2, number 15. I really like that one. It's a good question.
Wink, 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 wink.
All right, did I already do 9?
Let's do 15.
We did 15 in the notes, so you can go back and watch it from the website. All right, let's do 9 then. All right, so number 9, a 200-meter wide river flows due east at a uniform speed of 2 meters a second. So let's draw this thing. We've got a river that's flowing east. The problem tells us that it's 200 meters across. It tells us that the velocity of the water relative to the ground is 2 meters a second. Everybody good with what I've got so far? All right, it says a boat with a speed of 8 meters a second relative to the water. So the velocity of the boat relative to the water is 8 meters a second. It leaves the south bank pointed in a direction 30 degrees west of north. So let's see, 30 degrees west of north is going to be kind of this way, right? All right, now, is that vector that I just drew? That's the velocity of the boat relative to something. So the question is, relative to what? All right, now, the important word here is, this is describing the direction that the boat is pointed in. So the boat is pointed this way. The boat is pointed this way. Is it going to go that way?
No.
No, why not? Because the river is going to affect it, right? So this looks to me like it's probably a vector that represents the velocity of the boat relative to the water, right? Because relative to the ground, the water is going to push it downstream. Follow?
Yeah.
Everybody good? All right, so question A says, what's the boat's velocity relative to the ground? So the question is, what's the velocity of the boat relative to the ground? All right, any questions before we do this? All right, so to me, this is a good starting point. I guess we should identify that this is at 30 degrees, what did we say, west of north?
Yeah.
All right, so now that I've got this, what's my next step, you guys?
Write your equation.
Write out the vector equation that's been written up here on the board since forever ago, right? Okay, so let's see. The velocity of the boat relative to the ground should equal the velocity of the boat relative to the water plus the velocity of the water relative to the ground, right? Okay, well, let's see. The boat relative to the water, I need to split that up into components, right? So let's see, if we're going this way at 8 meters a second, here's my 30 degrees. This is the velocity of, what did we say, the boat relative to the water? So I need to find my two components. So the velocity of the boat relative to the water in the y direction, velocity of the boat relative to the water in the x direction. So this one's going to be -4. This one's going to be whatever 4 root 3 is. 6.93 thing. Follow or no?
Yes.
Okay, so that means then that the velocity of the boat relative to the water is -4I plus 6.93 J meters a second. Cool? All right, now the velocity of the water relative to the ground, that one's a little bit easier.
Positive.
Positive or -2I? What do you guys got?
Positive.
Positive. Isn't the river flowing east?
Yes.
So I think it's +2I. So now what do?
You
Add them up. Oh! So let me pause for a minute. Is everybody good with what I've done so far? Oh, darn it. All right, so let's see. That means then that the velocity of the boat relative to the ground is, let's see, -4 plus 2 is -2I plus 6.93 J meters a second. Good?
Yes.
And then now we can just put it all back together again, right? So let's see. We want an I component of -2 and a Y component of +6. So the velocity of the boat relative to the ground in the X direction is -2. The velocity of the boat relative to the ground in the Y direction is +6.93. And we're looking for the overall velocity of the boat relative to the ground. So Pythagorean theorem, and then a little bit of trig will get you this angle. E2. So it gives you 7.2 meters a second at 74 degrees north of west. Yeah, Sarah, what's up?
For clarity, when it says 29 seconds, not 28.
Yeah, hang tight on that for 1 second. Before I get to B, is everybody good with what we did here for A? Peter, that was that a triumphant, or was that a question, or what was up with the hands up? All right, are we good, you guys? All right, I think that the big takeaway that a lot of you guys had from this section was splitting it up into components. And I think when I did the notes, I did not do a good job of stressing that. Okay? Patrick?
Why did you say for B, 21 seconds?
Okay, so let's talk about B. It's okay, it's okay. All right, so question B wants to know how long it takes the boat to cross the river. There are two ways to solve this problem. All right? The boat needs to go 200 meters across the river, right?
Yep.
Okay, and the boat is going at 7.2 meters a second, right?
But not.
But not in the right direction. Okay, so what a lot of people did is for part B, a lot of people said, oh, I'm looking for the time. Oh, well, that's just displacement over velocity. And they said, oh, well, to cross the river, I got to go 200 meters, and I'm traveling at 7.2 meters a second, and if you do that, it gives you 28 seconds. But that's capital W wrong. Why?
Because you only are counting on y velocity to get across.
Yeah. So there are two ways to solve it. Option one is to figure out, option one is to figure out going at this, no, not that angle, going at that angle of 74 degrees, how far do you actually have to travel to cross the river? And it's more than 200, right? Okay? The easier way to do it is this. How quickly, according to my calculations here, how quickly is the boat making progress across the river? 6.93. Right? That's how fast the boat is making progress across the river, because that's the vertical component. What's wrong?
Nothing. Nothing.
I don't believe you.
We're fine. I'm just gonna come in after school with like a bunch of questions.
Okay, I'll be here with a bunch of answers. All right, and then the boat's got to travel 200 meters. Cool? So you just divide 200 not by 7.2, but by 6.93. Cool? And the reason I put that on there was because I didn't want you guys to get, 28, it's a rounding thing. So I was trying to highlight that you got to be careful. Sarah?
So if you get like 28.8, it's...
Yes. Yeah, whatever 200 divided by 6.93 is. Good? All right, this is the exact same thing, you guys, as like if you launch something horizontally and you want to find the time it's going to take to hit the ground, you use the vertical displacement, right?
Yeah.
Because you're interested in the time it takes to fall that vertical distance. How far it goes horizontally, we don't care about. Exact same thing. Cool? All right. We only got a couple minutes here left. Was there something else that you guys were... You a projectile problem?
Is this about the test difficulty, Mr. Or
This, I think, is pretty reasonable, yeah.
How about like number one?
Number one from what?
For the projectiles, or like just have floating areas.
Yeah, no, that's factoring wind resistance.
Yeah, don't worry about the 4-3B stuff, you guys.
How does it affect
So for projectiles, you guys, please make sure you're comfortable with the rules of projectiles. Horizontal motion is constant. Vertical motion is affected by gravity, so your vertical acceleration is negative 9.8. If you are given, so here, horizontally, there's only one equation you need to know. Okay? So if you know two of those values, find the third one. If not, don't look at horizontal, look at the vertical stuff. Okay? 99% of the problem solving in projectiles is looking at the vertical motion. Okay? So that's all the, the 1/2 AD squared and the 2a delta x and all that stuff. All right? I don't think we have time to do a whole problem. So we only got a minute here. Let me say this. I feel like the one thing we haven't talked about a ton since we learned it is the two-dimensional motion stuff. So, I guess, remember, it's kind of the same thing. You got to think about things in components, right? Look at your x motion, look at your y motion, but the equations are still all the same, right? So, like, if you want to find average velocity, for example, it's just your final position minus your initial position divided by time, right? Like, previously it was this. final position minus initial position divided by time, right? But just we use r now because you got to keep track of 2 dimensions. Okay? How do you find instantaneous velocity, you guys? Take the derivative of your x components and take the derivative of your y components and cool. All right. I think if you know this, the worksheet, and again, you can not worry about the 4-3b, but I think other than that, if you know this, I think you're in good shape. I'm around after school. I'm around in the morning. There you go. That's what I know.
So, Mr. Hecker,
Yeah.
packet for each of this page replacement with the other one.
Correct.